So here in this video, we're going to talk about from the very basic differentials. And so started with the total differential. So this is called a total differential. So that's a total differential. Suppose I have a function, let's call it f. It has two variables, so use the parenthesis x comma y. So this means f is a function of x and y. Now, if we take the total differential, which means we take df, because it has two variables, so it has two partial derivatives, which is partial f over partial x. We hold y constant, so we have dx like this. So that's our first term. The second term is partial f over partial y, while holding x constant. So we have dy like this. So this expression called total differential. It consists two terms, partial f over partial x and partial y over partial f over partial y. So this is called total differential. These two terms called a partial differential, or called partial derivative, to be more precise. So the partial derivatives, it has two parts, one in numerator, partial f, and denominator, partial x. The numerator is a function. Denominator is a variable. So you can see I have two variables. That's why I have two terms like these. So in other words, in our case, we have a partial f over partial x. So this is the one term. Another term is partial f over partial y. So we always hold one constant. Let me show you one simple example to start with. Suppose my function f has two variables. Again, one is x and one is y. If we want to calculate the partial derivative with respect to x, then it means that I'm going to hold y as constant. So this means partial f over partial x, holding y constant. So y is just like constant. When you take derivative with respect to x, it just equals 1. So therefore, I got the results for the partial derivative. Now, similarly, I can do partial f over partial y, and this equals x. So that is the first example. And we're going to work on more complicated situations. For instance, if I have f equals x, y, z like these. So now I have three variables, and I also can calculate the partial derivative. Let's say partial fx. Now I have to write them down. Which one is variable? So x is a variable, f is a function. So I hold yz constant. So like this, I hold yz constant. So I get x like that. Now second, sorry, the should be yz, forgive me. So that is yz like that. So yz is the constant. I can also take another derivatives. For instance, with respect to z now, so which means I'm going to take partial derivatives with respect to z. So I have something like this. So second derivatives going on like this. In this case, I hold my y constant and take a derivative with respect to z. So this z is gone, so I get y like this. I can take a triple derivative, which means I'm going to take with respect to y as well. So this will be partial, triple partial, and there will be partial x, partial z, partial y, and just equals 1 like this. So you can see things just pile up if we continue in take derivatives with respect to each other like this. For the moment, the example relatively straightforward. On the left, it's a function, right is its variables. But sometimes it's not that obvious. Let me show you another complicated situation. Suppose I have implicit partial derivative. This one's slightly more complicated. Let me show what I mean here. Suppose my function is called z equals x sine yz. So in other words, in this case, I cannot write in similar format like f equals x, y, z. Z here is a function. Now this is not simple now. So because this is the you have three variables, but z is a function, x, y, these two are variables. Now this time, suppose I'm calculating partial z over partial, let's say, y, like this, holding x constant. So how will I do that? Well, I'm going to take derivative of both sides with respect to y. So my left-hand side, my partial derivatives will be partial z over partial y. I hold x constant. Right-hand side of x is constant. I don't need to do anything with that, but the cosine term do. So I need cosine become x sine became sine become cosine. This would be cosine yz. Now from this on, we use a chain rule, which means consider yz as a new variable. It's called u, like that. So essentially u like that. So when we take the rule, will be partial u over partial y, and then you have another terms, partial u over partial z. I'm going to continue here. So first term will be partial u over partial y, which is take the derivative with respect to y. So I get a z here. Second term, I will keep y as a constant. Take partial derivative with respect to z to y, holding x constant. It will become something like this. Now I'm going to move this term, that term on the same side. It's basically I moved it to the left-hand side. So this gives me partial z over partial y minus xy partial z partial y holding x constant. I have xz cosine yz like this. So now I pull out these two terms exactly the same. So I have the coefficient 1 over x, 1 minus xy multiplied by partial z over partial y, and x equals xz cosine yz. So finally, I'm going to do both sides divide by 1 over xy. So this is 1 over xy like this. So then I cancel these two. So therefore my partial z over partial y just equal xz cosine yz over 1 minus xy. And that's the end of the instruction. And I hope you like this. And so it takes a few minutes, but it's not that hard. So I'm going to stop recording.